Okay, this is the fourth part of lecture 6, where I'm just going to be introducing the topic of non-steady state diffusion, and then we will go into it in detail for lecture 7. You might remember this image from the first part of lecture 6 when we talked about steady state diffusion. And steady state is defined as the condition where the change in concentration with position is constant, here and here. But at the surfaces and deep into the surface, or deep below the surface, the rate, these change in concentration with position are no longer linear, and so we have to use the non-steady state equation to describe that and to be able to predict the concentration at a certain depth. So the application here for non-steady state diffusion would be conditions such as, or processes such as carburization, where you diffuse carbon into the surface of a steel to make the surface stronger. Nitriding, it would also follow that same description in calculating or predicting the depth of hardness. And we have in this image for steel with carbon diffusing into the surface, what to expect as far as the impact toughness. That's this decreasing line here, the increasing ultimate tensile strength with the percent carbon, and the increasing hardness. You can see hardness and tensile strength are somewhat parallel in the lower concentrations of carbon. In real life applications, it would be rare that you would diffuse or create a concentration of carbon more than 0.8. And so the really practical part of this graph would go from here to here. And we can see that the toughness decreases. That's because the carbon increase can make the steel a little bit more brittle, but we can see that the hardness here and the strength here both increase, and they're somewhat parallel. So, for example, if we were asked to create a hardness of, say, let's see, in this case, 200 hardness rock will be, and we wanted that to a depth of 2 millimeters, then here's our hardness level 200. We would want to have at least 0.6 weight percent carbon or greater, just like here. Yeah, you're right. I was looking at the other side, yeah. So wherever this line of 200 meets the hardness line, you read down. Okay, so non-steady state diffusion it's predicted with this equation, which is a bit more complicated than steady state diffusion. But the numerator here is the difference between the concentration at some depth x and the overall concentration of in carbon of the steel, and the denominator is the difference between the concentration at the surface and the overall concentration. C sub s is the surface concentration. C0 is overall concentration, and sometimes that might be 0, but usually there's already some carbon in the steel. And then C sub x would be the concentration we're trying to achieve at a certain depth x. You've seen this term D before. This is diffusivity. at a given temperature, and lowercase t is time in seconds. Now, one process parameter that you don't see here is temperature, but remember that temperature affects this diffusivity d. Now, there's another function here that you might not have seen before, and this is called the error function, ERF. So, depending on what the value of x over 2 square root dt is, the error function of that value will get from a chart or a table, as in this next graph. So this is the error function table. And so if a value is, say, 0, then the error function of that value is also 0. But as this x increases, we can see that the error function increases until it reaches a maximum of 1.0. So the error function of x varies between 0 and 1.0 as x varies between 0 and essentially 2. Anything greater than 2, it will be, the error function of that value will still be 1. So when x is equal to 0, the error function of x, which is 0, is equal to 0. When x is 0, the error function is 0. When x is greater than or equal to about 2, the error function of x is equal to 1. And the error function of x never gets bigger than 1. And for our purposes, we are going to only be using this quadrant of the error function table. So you see in the next slide, we're only using this quadrant, and we have a table of values of, in this case, they call it z, but it works the same way. Here's the values of z, and the column next to that is the error function of the value. So when z is 0, error function z is 0. As z increases, the error function of z increases until we get to around 2, when it starts to have very little difference in error function of z with increasing z, and it never exceeds 1.0. Now, one thing to note, that there, for values, say from between here and here, for values of x between 0 and say 1.5, the values of error function of x change quite a lot. And which means that you can't you shouldn't use this table by rounding the value of x or z in order to determine error function z. In other words, let's say I have a z value of, say, 0.32. Between 0.30 and 0.35, which is where 0.32 is, there's a pretty significant change in error function of z. So to say, oh, well, 0.32 is close to 0.30, I'm just going to use this value, wouldn't give you a very accurate value of error function z for your equation. So that's why I say you've got to interpolate. Once you get to, say, above maybe 1.4, and certainly once you get to above 2, the change in error function z gets really small with increasing z. And at that point, you really don't need to worry about interpolating. So I just want to talk about the limits here of how big and how small the values of c sub 0 and c sub x and c sub s could be. So on one extreme, we could say as temperature increases, If temperature increases, then as T increases, diffusivity increases. We knew that from before, from last lecture, or the last part of this lecture. And if D increases, then the denominator 2 square root dt, lowercase, must increase, right? And as 2 square root dt increases, then x over 2 square root dt must decrease. Yeah? So as temperature increases, this whole quantity x over 2 square root dt decreases. And the smallest that this could get would be 0. So if x over 2 radical dt is 0, that's the quantity that we're operating on with this function. If that value is 0, we know that the error function of that value is also 0. Oops, gotta get an x there. 2 square root dt. Okay, so if this whole quantity, error function of x over 2 square root dt, if that approaches 0, then 1 minus error function x over 2 square root dt would approach 1. Which means the only way that this quantity can equal to 1 is if the numerator and the denominator are equal. So that would be where Cx minus C0 would be equal to Cs minus C0. So this is where C sub x approaches the surface concentration. So at high temperatures, the concentration at depth x approaches the concentration at the surface. Concentration C sub x approaches the concentration at the surface. That's for temperature increasing. For time or duration increasing, we have the same sequence of events. As time increases, then the quantity x over 2 square root dt must decrease. And then you can follow the logic further to the fact that C sub x would equal C sub s. So at high temperature, the concentration at depth x approaches surface concentration, also at long duration. Where time approaches infinity, C sub x approaches C sub s. So this process involves having a steel and putting it in close contact with carbon. If this was a solid carbon or graphite, this would be called pack carburization. So we put carbon in close contact with steel and we apply heat. And at the surface, there's a concentration C sub s. And as we go deeper into the steel, we can measure C sub x. And so if temperature is high, which affects diffusivity and makes it high, or if time is long, then the concentration at depth x will approach the concentration at the surface. Okay? The other extreme is if we're looking at the depth. If we increase the depth into which concentration is measured, that depth is x. So as x increases, x over 2 square root dt increases. And if x over 2 square root dt increases, that's the value in this case of z, then error function of it approaches 1. As x increases, so does x over 2 square root dt, which means that error function of x over 2 square root dt approaches 1. And if that happens, if this term approaches 1, then the right side of the equation approaches 0. And the only way that can be true is if C sub x is equal to C sub 0. If the concentration at depth x is equal to the overall concentration before you started, which means that as we go deeper and deeper into the surface, as x increases, we approach the point where the diffusion hasn't gotten and the overall concentration has not been increased. So those are the two ends of the sort of extremes of non-steady state diffusion. We can go to high temperature and long time, and the concentration at depth x approaches the surface concentration. And then as x increases, the concentration at depth x approaches C0. We'll get into more detail and work these problems next time.